So, very good morning to all of you. I'm Dr. Krupa Rasane, Professor at ENC, Jain College of Engineering, Belgaum. So, let us continue with Power Electronics third module, the eighth video of the third module. In this module, we'll be looking into the AC voltage controller, the principle of phase control and single phase controller with resistive and inductive load. This is prescribed in the textbook, as the textbook referred as to the syllabuses Mohammad Rashid. So in this video, basically, we'll be looking into the principle of phase control. In that, we have already completed with the single phase half controller, and we'll be now moving on to single phase full controller with resistive loads. And also we'll be looking at the derivation of an expression for RMS value of the output voltage when the load is resistive. So looking into the single phase full wave AC voltage controller using AC. We call it full wave because you can see there are two thyristors connected. In half wave, we had a single thyristor T1 connected and T2 was a simple diode. And since diode cannot be used as a controlled rectifier, we call it as a half wave controlled, which is controlled by the T1. In full wave AC voltage controller, we'll have two SCRs, T1 and T2, and the load in this case will be purely resistive. Okay, so single phase full wave AC voltage controller circuit using two SCRs or a single triac. Even a single triac can be used, and instead of T1 and T2, I can replace it with a triac. I'll show you the figure later. The AC volt power control flow to the load can be controlled by T1 in the positive half cycle and for the negative through the T2 half. So both the half cycles are being controlled, and the both of them can be controlled with the firing angle or triggering angle alpha. Then the RMS value of the load voltage can be varied by varying the triggering angle alpha. So single phase full wave AC voltage controller using SCRs. So here we see that the input supply current is alternating in the case of a full wave AC voltage controller, and due to the symmetrical nature of the input supply current waveform, there is no DC component of input supply because we are getting both the positive as well as the negative half cycle. And both the areas of positive half cycle is equal to the area of the negative half cycle. So no DC component of the input supply current. That is, the average value of the input supply current is going to be 0 because the positive half cycle will cancel out with the negative half cycle of the current. A single phase full wave AC controller with resistive load is shown, as we have just seen, and it is possible to control this AC power flow to the load in both the half cycles by adjusting the triggering angle alpha. Hence, the full wave AC voltage controller is also referred to as bidirectional controller. Single phase AC full wave AC voltage controller using SCRs. The thyristor T1 is forward biased during the positive half cycle, right? And the thyristor T1 is triggered at an angle of alpha that is from 0 to pi radians, 0 to 180 degrees or pi radians. Now consider the on thyristor T1 is an ideal closed switch with the input power supply being given, right? 1 second. The thyristor T1 is triggered at an angle alpha from 0 to 180 degrees. Considering the on thyristor T1 as an ideal closed switch, the input supply voltage appears across the load resistance R, and the output voltage is same as the input voltage, that is Vs, and that happens during the time when omega t is alpha to pi radians. The load current flows through the on thyristor T1 and through the load resistance R in a downward direction during the conduction time of T1 from omega T is equal to alpha to pi. Okay. So when T1 is on, the load current will flow through the load resistor, right? In the downward direction. That is, you can see this diagram in this direction, downward direction. And when T2 is going to conduct, the current through the load will obviously will flow through the upward direction of the art. Since both the cycles are going to be there, right? We are going to get the AC cycle. So T1 will conduct from alpha to pi radians. Okay. And at omega t equal to pi, what happens is the input voltage becomes zero and the thyristor current which is flowing through the load resistance R also falls to zero. And hence T1 gets naturally turned off. No current flows in the circuit during omega t equal to pi plus alpha. Why? Because both the thyristors T1 and T2 are in off state. So T1 is on only during alpha to pi whenever the load is resistive. And even though the T2 is forward biased in the negative cycle, it is not yet triggered and it gets triggered only at pi plus alpha. The thyristor T2 is forward biased during the negative half cycle, right, of the input supply. And when thyristor T2 is triggered at a delay angle alpha pi plus alpha, then the output voltage follows the negative half cycle from omega t equal to pi plus alpha to 2 pi. So when T2 is on, the load current flows in the reverse direction, that is upward direction, as I told you, through T2 during omega t equal to pi plus alpha to 2 pi radians. The time interval spacing between the gate repulses of T1 and T2, this is T2, is kept at pi radians or 180 degrees. Okay. So the spacing between the triggering pulse for T1 and the triggering pulse for T2 is kept at 180 degrees. At omega t equal to 2 pi, the input supply voltage falls to zero, and hence the load current also falls to zero, and T2 turns off. Single phase. Now, I had told you that T1 and T2 would be replaced by a single triac, which is a bidirectional device. And when the input is positive, the current will flow from top to bottom in RL. And when the input is negative, the current, and this is positive, the time current will flow in the reverse direction through this device. And this device can be popularly replace the two SCRs, which were shown earlier. Now, when you come to single phase, see whether it is SCR or triac, this is the input that we are giving at the circuit. And since it's a resistive load, this is the output we're going to get. When the input is VM, right, and from it is going to be triggered at alpha. So T1 will be forward biased and get triggered at alpha, and it will carry the voltage up till pi. When the input reverses here, right, when the input reverses here after pi, T1 is going to be reverse biased and turns off here. So you see this is load current that will flow through T1 when it is triggered at alpha. So from alpha to pi, you are going to have the input same as the output, same as the input. But from 0 to alpha, there will be no output. Again, during the negative half cycle, T2 is going to be forward biased, but it will be triggered only at pi plus alpha. So at pi plus alpha, it is going to start conducting, and it will conduct till 2 pi till the input becomes 0 and goes in the positive. Once it goes in the positive, T2 is going going to be reverse biased, and there will be T2 will become off. Again, it will wait for T1 to be triggered at the next alpha. So the difference between the two firing gate pulses. So you see, so for T1, if I give the firing pulse here, I'm going to give T2 at an angle of pi plus alpha. So the triggering pulse difference between these two T1 and T2 will be pi. This is the input equations for input supply voltage. Vs equal to Vm sin omega t, that is root 2 Vs sin omega t. Output voltage across the load RL can be written as V naught is equal to same as VL, that is Vm sin omega t. Okay, for alpha to pi because T1 conducts, and from pi plus alpha to 2 pi because T2 conducts. So the output load current can be given as V naught by RL, right? And which is equal to V naught is Vm sin omega t by RL. And this Vm by L can be written as Im sin omega t. So the output will be, the load current will be same as the input supply current from omega equal to alpha to pi and omega t equal to pi plus alpha to 2 pi. So to derive an expression for the RMS value of the output load voltage, we have V naught RMS squared equal to V naught V naught L, that is the load RMS, equal to 1 upon 2 pi, 0 to 2 pi, one cycle we take VL squared d omega t. Okay, and since I'm taken V naught squared here, I can do away with the root sign here. For a full wave AC voltage controller, we can see that the two half cycles of the output voltage waveforms are symmetrical. Hence, the positive and negative area will be same, and the output pulse time period or the output pulse repetition time is pi, right? So hence, we can also calculate the RMS output voltage by using the expression given below. VL squared equal to 1 upon pi 0 to pi Vm squared sin squared omega t, right? So since I'm 0 to pi, if I take 0 to 2 pi, I will substitute it as by, okay. So now I'm putting upon 2 pi, 0 to 2 pi, VL squared d omega t. So since VL is equal to V naught is equal to Vm sin omega t, I can do two integrations. One is from alpha to pi, right? And the other is pi plus alpha to 2 pi. Because from pi to pi plus alpha, there will be no signal, right? So from alpha to pi and then pi plus alpha to 2 pi. So we square the unit, right? And this is still VL RMS squared. Let us solve, so this will become sin squared. Vm squared is taken out. Same here, Vm squared is taken out and we have sin squared term here. So let's take Vm squared outside the bracket itself, and we can replace the sin squared omega t with 1 minus cos 2 omega t by 2. And similarly here, 1 minus cos 2 omega t by 2. We know that this again can be split into two. One will be 1 upon 2. So let me get this 2 outside. So we get 2 pi into 2, right? And this will be integration of d omega t minus integration of cos 2 omega t between the limits alpha to pi plus pi plus alpha to 2 pi integration of d omega t minus pi plus alpha to 2 pi cos 2 omega t d omega t. So this is again Vm squared by 4 pi, and substituting the values of for omega t for alpha pi, right? So same thing here. Then we are integration of d omega t will be omega t, and here also the integration will be omega t. For pi plus pi to alpha, cos of sin cos 2 alpha becomes minus sin 2 omega t by 2. Okay, so substituting likewise and solving, I will be getting an expression of this time. Now, when I get this expression, please try and do it yourself so you get to know that you understand the problem. It's a simple substitution problem once you come to this level. So Vm squared by 4 pi. So this is both 2 into pi minus alpha minus half sine of 2 pi is 0 minus sine 2 alpha minus sine of 4 pi is again 0, right? Minus sine 2 pi plus alpha. So substituting, I'll be getting Vm squared by 4 pi 2 into pi minus alpha plus sine 2 alpha plus sine 2 of pi plus alpha by 2. So solving this, a simpler function, right? I will be getting this expression sine 2 alpha by 2 plus. Now this is, a like sine of a plus b. And doing that, I'll get sine into cos plus cos into sine, right? And we know that sine of 2 pi is 0 and cos of 2 pi is 1. Again, substituting that, I'll be getting Vm squared by pi 2 into pi minus alpha plus sine 2 alpha by 2 plus this whole term becomes sine of 2 alpha divided by 2. Okay. So I'll be getting an expression Vm squared by 4 pi 2 into pi minus alpha plus sine 2 alpha. Right? This together becomes 1. And here I'll get Vm squared by 4 pi 2 into, so bring the 2 inside. Right? So substituting, I'll take away the square from here and I'll put the square term here. So this Vm squared becomes Vm, 4 pi becomes 2 into root pi, and the whole thing under the root sign. So continuing with the solution, Vm upon root 2 into root 2 pi, right? So this also we have to consider. This root 2 into root 2, 2 can be written as in that fashion. And then 2 pi minus 2 alpha as it is. Get this 1 upon 2 pi inside, right? This inside. And substitution, I'm getting Vm by root 2 inside it 1 upon 2 pi. 2 is outside minus alpha plus sine 2 alpha by 2. So the RMS load voltage will be Vm by root 2, root of this 2 cancel. So 1 upon pi minus alpha plus sine 2 alpha by 2. So the load RMS can be further written as Vm by root 2 can be replaced with input RMS, VI RMS, and this term remains as it is. So I can write that VI RMS is nothing but the supply RMS, VS, right? And now once I get this, the maximum RMS voltage can be applied to the load when alpha is 0. It is true because alpha can be varied from 0 to 180 degrees. So when I give alpha is 0, means the whole wave is going to come, half wave will be coming at the output. So I expect maximum RMS voltage in that case. Okay. And hence, output is going to be Vm by root 2. And as alpha is increased, the RMS load voltage is going to decrease. So as alpha increases, output voltage decreases, right? Because the voltage that comes at the load will be less than the half wave. So this is the value of RMS voltage when alpha is 0. So I substitute in this formula, right? So alpha I put 0 and this is sine of 2 into 0 upon 2. So solving this, I'll be getting output voltage, which is Vm by root 2, and that is same as the supply. So if alpha is 0, I'll be getting the same output, half cycle. So the output control characteristics for a single phase full wave AC voltage controller with resistive load can be obtained by plotting the V0 RMS. So this is the control characteristics for the single phase full wave AC voltage controller, right? Full wave again. So let us look at the control characteristics. So what happens when alpha changes? So the control characteristics is the plot of RMS output voltage V naught RMS versus the trigger angle alpha, which can be obtained by using the expression for the RMS output voltage of a full wave AC controller with resistive load. So V naught RMS is Vs under the root sign. This is the formula that we have got, right? And we have got, okay, one second. And where Vs is Vm root 2, which is equal to RMS value of input supply voltage. So we get the trigger angle alpha in degrees. So I am changing alpha from 0 to 180 degrees, and the angle in radians can be equally written. 30 is pi by 6, right? 80 means pi by 2. So likewise, this is another column for alpha in radian. And when I substitute this value in the formula that we have just derived, right, this formula, then I'll be getting a value. So if input triggering angle is 0, I'm going to get the whole of the half wave at the output, positive as well as the negative. And I get 100% of the input. If I change alpha to 30 degrees, right, then I'll be getting only 0.9854 of the input voltage. And if you look at the percentage wise, it becomes 98.54%. So likewise for 60 degrees, 90 degrees, we go seeing that as I increase alpha, right, from 0 to 180 degrees, the output percentage also is decreasing, right? And when alpha is 90 degrees, you can note that output is equal to 0. So as alpha is changing from 0 to 180 degrees, the output is changing from 100% to 0. So the maximum voltage occurs when alpha is 0, and the minimum voltage occurs when alpha is 180 degrees or pi radians, right? So this is exactly the curve that we have to see. So we have this AC voltage controller. We have plotted V naught RMS versus the triggering angle. As alpha increases, that table what we have just plotted with using the formula, if I plot it here, you can see that the output RMS is highest when alpha is 0 and is least when alpha is 180 degrees. So I get this kind of a waveform for the full wave AC voltage controller with the resistive load. Now, when I compare it with the half wave AC voltage controller, we can notice from the previous slide figure that we obtain a much better output voltage, much better output control characteristics by using a single phase full wave. In half wave, the control is only from 0 to 180 degrees, whereas here the control is from 0 to 2 pi, because we have two thyristors. There we have a single thyristor. So the RMS output voltage can be varied from 100% at alpha equal to 0 to a minimum of 0 at alpha equal to 180 degrees. Thus, we get a full range of output voltage control by using a single phase AC voltage control. So coming back to this particular video, we have been looking into the principle of phase control. And in this earlier video, we had done single phase half wave. In this video, we have looked into the single phase full controller with the resistive load. We have also done the derivation of RMS output voltage in this particular video. Okay. And with this, I would like to thank you. Thank you for your patient listening. If you have any doubts or queries, please get back to me. Thank you so much.